Today we're going to talk about inverse functions. Now again, you've probably seen inverse functions, but you've probably seen them with regards to the real numbers only. So we're going to talk about them more generically and as they relate to relations, and then look at some properties of them. So when we have a relation from a set A to a set B, we've already said that an inverse relation from B to A is defined as the set of all elements BA when AB was an element of the original relation. So if we had a set A of the letters A, B, C, D, and a set B of the numbers 1, 2, 3, and a relation that was defined as the set of ordered pairs A1, A3, C2, C3, and D1, then we have a relation from A to B. That is our relation. Now the inverse is taking all of those ordered pairs and reversing them. So the inverse relation that corresponds to that one is the set of ordered pairs 1A, 3A, 2C, 3C, and 1D. Now, all relations have inverse relations, and functions are relations, but functions have some special properties about them. So we have the question of when is the inverse relation, that is the inverse of a function, actually a function itself? So we can think about it, and in order for an inverse function to be a function, well, its domain has to be all of the elements in the set B. Well, that means that the original function itself, f, must have mapped to every element in B. So that means that f must have been an onto function, or a surjective function. Well, also, if we think about the case where f is not a one-to-one function, or not injective, then we have the case that f of a1 equals f of a2, which equals b for some a1 and a2 in A and b in B. So a1 is not equal to a2. Well then, if we think about the elements in the inverse relation, we have elements ba1 and ba2. Now remember, a function takes every element in the domain and maps it to a unique element in the codomain. So since ba1 and ba2 are both a part of the inverse relation, and a1 does not equal a2, then our inverse relation is not a function. So that means that f must also be one-to-one if our inverse is going to be a function. So we're going to use that idea along with the idea that f of a equals b if and only if the ordered pair AB is a part of the relation that is my function f, and if f inverse is a function and f of a equals b, then the ordered pair BA is in the inverse relation f inverse. So the ideas that we had generated previously along with these two give us basically this theorem that we have the idea of a proof already done for, where we let f be a function from A to B, then the inverse relation f inverse is a function from B to A if and only if f is bijective. Furthermore, if f is bijective, then f inverse is also bijective. So we also have a theorem that tells us that if we have a function f from A to B, then g from B to A. So we have these two functions, and notice the codomain of f equals the domain of g. Then we can compose these functions, g of f, and we get what's called the identity function on A. And if we compose them the other way, we get f of g is the identity function on B. Namely, it's the function that takes every element from itself to itself in the same set. So then f and g are bijective, and g equals f inverse So if we compose a function with its inverse, then we get the identity function on the set. So let's take a look at an example of how we might find an inverse. So here I have a function. We've already shown that this function is bijective. So we have f of x equals 3x divided by x minus 2. And we're going from the real numbers without the element 2 to the real numbers without the element 3. Now, we know that f composed with f inverse of some element x equals that element x for all elements in our domain. So we're going to use that fact. So we have f of f inverse of x is going to equal 3 times f inverse of x divided by f inverse of x minus 2, which equals x. And then what we're going to do is we're going to solve for f inverse of x. So going through the steps solving for f inverse of x, we eventually arrive at f inverse of x equals 2x divided by x minus 3. Now, a special type of bijective function that we have is a Now, a special type of bijective function that we consider sometimes is called a permutation. Now, a permutation on a non-empty set A is a bijective function on that set A. So any function from a set to itself, like this one here, that I have f of x equals 3x minus 5, that's a permutation of the real numbers. Now, let's consider a smaller set than the real numbers. So say I have the set A, consisting of the numbers 1, 2, and 3. Now, a permutation of A is going to be a bijective function from A to A. Now, if you think about it, the element 1 in my set A can map to any of the 3 elements in A. Well then, the element 2, since it's a bijective function, can map to any of the 2 remaining elements in A that 1 did not map to. And the element 3 then must map to the 3rd and final element. So there are actually 3 factorial, or 6 different permutations on my set A. So one of these functions is going to be our identity function, mapping 1 to 1, 2 to 2, and 3 to 3. Another possibility is that I map 1 to 1, but then 2 maps to 3, and 3 maps to 2. So we can write these permutations as sets of ordered pairs as relations, like we do, or we can represent them instead with these parentheses with the elements of the set A written across the top, and then below them we'll write their images. So if I do that, here are the 6 possible permutations of the elements 1, 2, and 3, that set A. Now, if I compose these functions, then I am looking at taking, say, 1 goes to 2, and then 2 goes to 3. So 1 will go to 3. Likewise, if I look at where 2 goes, 2 will go to 3, and then 3 will go to 2. So 2 maps to 2. And then 3 maps to 1, and 1 maps to 1. So 3 will map to 1. And that is a 3. So what we actually see is when we compose any 2 of these permutations, we actually get one of the other possible permutations. Now, we can do this with composing even more than just 2 of them. And we'll notice that sometimes when we compose 2 of these permutations, we're actually going to end up with our identity permutation, the one that maps 1 to 1, 2 to 2, and 3 to 3. And these are inverse permutations or inverse functions of one another. Now, one of the ways that we can find the inverse very quickly is I can take a function that I had, say I want to take the inverse, finding the inverse, I just flip the bottom numbers and the top numbers, and then I reorder according to the top numbers. So my alpha 5 permutation was the one that mapped 1 to 2, 2 to 3, and 3 to 1. So its inverse is going to map 2 to 1, 3 to 2, and 1 to 3. But this is not the way I write a permutation normally. Instead, I want 1 to be in the top left position, so I move the column 1, 3 all the way to the left. So I get 1, 3, then I move 2, 1, and then 3, 2. And I notice that this is my permutation alpha 6. Now, we already noticed that there were 3 factorial permutations when I had a set of 3 elements. There are actually n factorial permutations on the set 1 to n, and we denote this with this script s with a subscript n. So we've already seen that s sub 3 equals my set of permutations alpha 1 to alpha 6. And we've seen that when we look at all of the elements in this set, they actually are closed and associative property holds, and they all have inverses as well.